Good morning, ma'am. Good morning, everybody.
Good morning, Ashutosh ji.
Sir, very good morning.
I have joined.
Oh, yes, sir. I have seen you. Hemavati ma'am and Priyanka ma'am. Are you able to hear me? I think when you are hearing, sir, they must be. But my request is kindly switch on your camera so that we can start the program. Yes. Now I can see Priyanka ma'am. Can you please unmute your mic? Oh, I think you are not able to see the mic. Then what you do, you just, yeah, now I think you can speak. Are you able to hear me? Okay, but I am not able to hear you. What you do, you just disconnect and again, please join. And Hemavati ma'am, are you able to hear me?
Good morning, sir. Can you hear us now?
Yes, ma'am.
Okay. So, should we start?
Sir, presenter का okay? Shall we share?
Sir, you are not.
ठीक है, thank you. इसमें कौन से हैं?
I think stop. Pen and knee help. Start first lenses.
Yes, I can very well hear you, ma'am.
Okay.
Please check whether you can see the presentation slides or not.
Just a minute. We'll make you the present. Oh, yeah, you are already presenter, so you can share your screen.
No.
But
Please allow Priyanka ma'am to be the presenter. I will be sitting along with her.
okay, so both of you are at the same place.
Yes,
Yes.
we are at the same
Very good.
place.
So that means okay, at one place you are doing it. Very good, no problem. So that means both of you are together, and we can hear you. We can see the video.
Share camera.
Please share the screen.
Yeah.
This one, no?
Yes, please.
This one.
This.
Sir, can you see this?
Yes, ma'am.
Okay.
Please start the PPT.
Is that visible? I'm changing it.
No, ma'am. Only the USB drive showing. Open the PPT.
It's already open, sir. It's showing me that WebEx is sharing a window.
Please unshare and share again.
Okay. Stop sharing. I will share again. Mine.
Ma'am, can you share? Can you check your? Yeah, please. Now I think yes. Now your presentation is there. We can see your presentation. Kindly make it in the presentation mode. It is not in the presentation mode. Yes, but it is outside of the. Okay, now it is okay. Very good. But again, we are not able to see you in the presentation mode. We are able to see all the slides and the left. If you can make it in the presentation mode, it will be better. Otherwise, yeah, now it is okay. Very good. And slides are just move on another slide or reach at the first slide. First slide, please. First slide. Okay, very good. So now it is okay. We are able to see your slides. It is in the presentation mode, and you are also able to move the slides. Now I think, ma'am, it is okay. Can we start?
Yes, sir.
Thank you very much. Good morning to all. As we are aware, today we are having the subject which is very important for the laboratory's point of view, for the industry's point of view, the direct current and the impedance parameters, which are very important for the electrical metrology. National Physical Laboratory, we have the scientists from the National Physical Laboratory who are working on these in these fields. And I hope that this particular seminar will be very useful for the industries, for the students of the engineering colleges, as well as the enable labs who are doing the calibration or the testing of the electrical parameters. So, ma'am, thank you very much for accepting our request and being holiday to share to give us your precious time. We are thankful to you. Welcome to all. So first of all, we have with us our Honorable Director Sir, Shri B.N. Dikshit Sir. I would like to request him to kindly inaugurate the workshop, please, sir.
So, Ashutosh ji and Madam Jain and other people who are participating in this very program, I feel privileged to inaugurate this very session. And the subject matter is very good for the calibration of the electrical items and so many other things. So in legal metrology, there are the lot of the things where people do the calibration work of the electrical items also, particularly in the model approval test. There are the lot of electronic equipment, because now these days most of the things are uh, running through the electronic mode also. So there is need of electricity and various parameters. So these required to be checked. And I hope that these seminars will be very fruitful for all the legal metrology officers, manufacturers who are manufacturing various type of weighing and measuring equipment, and the peoples who are in the field of the calibrations of electrical items and the laboratory like RRSL, etc. And the students who are participating in this very program, they can also make the different type of project and all that very things. Thank you, Astosi, and thank you, um,
Thank you very
uh,
much, sir. Sir, these are
speakers.
very important actually equipments, and
Mm.
we are also planning to have the primary standards of current ampere in regional reference standards laboratories at the five corners, five geographical regions in the country. With the help of the National Physical Laboratory, we are planning on it, and certainly it will enhance the capabilities of the industries and the laboratories in the country if we will be able to do that. Because right now, as I know, when I was discussing with the NPL scientists, they basically the voltage and the resistance, they have the primary, and with the help of this voltage and the resistance, we are developing the primary of current ampere. So, but we hope that the primary standard for the current will also be very soon developed. With this, I would like to request our honorable speakers to kindly enlighten us with their knowledge, with their experience, and share with us about the electrical parameters of these electrical metrology of these DCs, DC, and the impedance parameters. Over to you, ma'am, please.
Good morning, all of you. I hope you all know about DC and impedance parameters and DC metrology. You must have listened about it. So today, I will try to put the insights on this subject so that you will be more familiar with all these terms. So starting with the workshop topic is the DC and impedance parameter of electrical metrology. So first I will explain what is NPL and what is a metrology institute and what is the role of NMI in the development of a country. So so outline of the presentation will be role of the NMI, the growth engine of the nation, metrology and its impact to the society, metrological traceability standards, global metrology infrastructure, DC metrology, high voltage DC metrology, impedance metrology, coaxial impedance bridges, and services to the nation. So, first of all, I would like to tell you the NPL is established before the independence. The first foundation stone was laid down on the 4th January 1947 by the Prime Minister of India, Pandit Jawaharlal Nehru. So, it's inaugurated in June 20. Since then, we are serving the nation with the different primary standards and standards of units. So, NPL is the custodian of electrical standards or all seven base unit, SI unit, that is International Systems of Units, as a part of Act of Parliament. So, the just a minute. So, as per the Legal Metrology Rule 2011, the General Conference of Weights and Measure means the conference decides the Meter Convention of India, which was established in 1957, and we maintain seven base units since then up to the today's era. So now I will put what is the role of an NMI. So NMI is the custodian of national standard, as I have already told you. And NMI is the growth engine of the country, which provides the science behind the national quality infrastructure by standardization, metrology, testing, certification, and accreditation. So now you can see here, these are the seven base units, and these base units are defined by the constants. This is all seven base constant which define the electrical units, all the base units, all seven base units. So the role of NMI to provide the traceability to the SI, maintain and develop primary standards, research capability to achieve the compatibility at international level and maintain the same, and calibration services and training and advisors. So this is our role, NPL is also a member of CIPM MRA. So whatever is calibrated here, these certificates are accepted at everywhere. So I will explain brief about all these things which you are listening here. I will explain one by one. So metrology and its impact to the society. Before starting the metrological terms, I would like to go your insight of our electrical standards metrology division of CSR and TEL via short video. So
Why do we measure things? To allow trade, to build trust and confidence in the society, to advance the technology, to make environments safe, and live better quality of life. Welcome to Electrical and Electronics Metrology Division at CSIR National Physical Laboratory. Is the custodian of national standards of electrical and electronic parameters, which involves voltage, current, impedance, power, energy, and quantum standards. Metrology is the science of measurement. We think, we feel, but how accurately we measure the things is the requirement of this modern age. This division offers apex level of calibration primarily for quantum Hall resistance, low frequency and high frequency impedance, DC voltage and current, DC high voltage, AC high voltage, AC high current, AC power and energy, and testing services for energy meters, which are internationally recognized. Research efforts on another side for quantum standards are of quite interest specifically. Quantum current, quantum resistance, and quantum nanophotonics laboratory has vast infrastructure and facility, which aims for detection of photons using the novel concept of superconducting nanowire single photon detectors. Team also putting major efforts into realization of quantum current standard using single electron tunneling and quantum phase slip phenomenon. Laboratory also started the growth of epitaxial graphene anchored on silicon carbide to realize unit of resistance based on graphene. Experts of division also involves in designing and synthesizing materials for development of sensors using pulsed laser deposition as well. Laboratory has a significant role to play by bringing technologies and measurements traceable to SI units for smart applications such as smart grid and electric vehicle grid integration. CSIR-NPL helps the Indian industries to enhance their manufacturing and export, thus contributing to the GDP of the nation. Contact us to know more about us.
So this is the brief what we are doing at NPL. Dr. Ashutosh has already mentioned we are deriving the current from the voltage and resistance, but we have started to work in the field of quantum current standards. So we have shown you the facilities which we are working for to develop a new quantum current standard at India. So moving forward, what is metrology? I think before this video, you have clear why metrology is important. Important isliye because it affects our daily life. If you have all the things, if you have a meter and you are measuring here and you are measuring meter at some other country, if there is a difference, then what will you will do? You cannot metallize the things. So measurements is very important, and role of the NMI is to realization of the units with the primary base units. That is, these are the SI units. So metrology is a combination of definition of SI units, scientific measurements, measurement for trade, that is legal metrology, so to remove the trade barriers, and applied traceable measurement for industrial production, dissemination of units through traceable calibration, and system of fundamental constants like electrical charge, Planck constant, Boltzmann constant. We define the SI unit with reference to these constants to provide the precise measurement. Metrology also includes all theoretical and practical aspects of measurement, including the measurement uncertainty and its fields of application. These are the some basic terms which you hear in day-to-day life. What is accuracy, precision, repeatability, reproducibility, random errors, systematic errors, measurement results, uncertainty, and traceability. From here you can see this. The first one, first is accurate and precise, because you getting all the measurements within this limits, that is close to the true values. Here you are getting repeatable measurements apart from the true value, but it is repeatable. So it is not accurate, but it is precise. Similarly, you can see here these values are close to true values, but it is not precise. And these are value are scattered all around, so these are not accurate and not precise. So whenever you have random errors, you will not get the accurate results. And if you have systematic error, your precision and accuracy will be affected. So metrology is the science of defining all these terms, which we can at NPL India, we are providing the most accurate and most precise measurement in the country, and our measurements are acceptable everywhere because we are the National Metrology Institute of India, and our services are best in India. And we are comparable to other leading NMIs like NPL UK, PTB Germany, BIPM, and all NIST USA. All these laboratories' results are comparable to our results. So we are also contributing to remove the trade barriers whenever you require to sell something. So industry person come to us to measure how accurate we have developed this product. If we certify it is accurate and you can go ahead, so they can increase their business all around the world. So this is the role of metrology and role of the NMI. So this is you have hear about the traceability. What is traceability and what is metrological traceability and how standards are related to these. So first of all, you have seen the base unit. SI units are international system of units to harmonize all the standard all over the globe. So SI units on the top of the traceability triangle. So these are the 7 base units. Now NMIs and designated institutes. DI represent the designated institute from the BIPM. So NMI and designated institute maintains and develop the primary standards or reference standards, which is required to link the SI units with their measurements. So we are on the after the SI units, we have all the SI units, then verification authorities like NABL in India, and calibration and testing laboratories which are accredited by NABL, and we have regulated, that is legal metrology part, and voluntarily which customer we want precise measurement results. So this is the traceability chain, how we link their standards. These are the product and services. We are linking these standards to the primary standards. So this is our role to support the Indian industry and research. So here you can see, if you visit our NPL campus, we have this traceability triangle positioned in our campus. So CIPM MRA on the top, CSR NPL, then in the second position to maintain all the SI based units, then accredited laboratories and strategic sector, public sector comes into the picture, which maintains their reference standard to disseminate traceability to other industries throughout the country. Then manufacturers and end users are coming at the last. So here, whatever product is developed by any manufacturer or any end user, how accurate it is, we are defining it with linking these standards to the SI units. So the unbroken chain of measurement for the quality infrastructure of India. So to maintain the quality of life, to improve our quality of life, we have to improve our standards, and we have to maintain our standards at par with other international laboratories. What is a meteorological? Some image is not visible. I don't know why. So, what is a physical standard? If you think about, I talked about NMI standards, traceability, all these things. Now, one question comes into your mind: what is standards? So, standard is if you have a unit, you should have some material, some things to realize these units. These are a physical standards. फिजिकल स्टैंडर्ड्स कैन बी एन आर्टिफैक्ट, कोई आर्टिफैक्ट हो सकता है, जैसे कि अगर आप डेली लाइफ में देखें, सो यू हैव वेट, किलोग्राम वेट which you use to measure things. It is a natural phenomena. It can be a natural phenomena, like if you talk about the frequency standard, so you can you know it, the frequency is defined in terms of the hyperfine stages of cesium atom. So it's a natural phenomena which define the frequency standard. Similarly, standardization process of measuring anything is also like ASTM standard defined by the BIS for measuring some parameters. So So these all are called the standards. So sir, can you hear us? I'm not able to show
Yes,
you
ma'am.
the.
Very well. We can hear you.
But can you see the image there?
Yes, we can.
Where you can see some image, because I'm not able to see here.
No.
No, no. Sir, we will show it later. No, there may be some
Okay. No
technical
problem.
issue.
Please. Please.
So as I here I have put one slide which they define the all 7 base units. Then unit derived from these quantities like meter, mole, candela, kg. These are the 7 base units, and voltage, current, all these comes as a derived unit. But how these are interrelated, this was the image. I will show at the end of the slide. Everywhere it's a problem. These are very important images. I don't know why it's not coming here.
Yeah,
I will try.
ma'am, slides are not visible actually.
Any slide you cannot see?
Ma'am, what you can do? You just share me the presentation.
Okay, okay, that will
We
be
will
fine.
start. Santosh ji,
Yes, sir.
can we share it from here?
नहीं सर, एक्चुअली में पीपीटी में कहीं इमेजेज का है, ये इमेज नहीं आ रही है.
हाँ,
इन द लिंक ऑफ इमेज.
Okay. So that means if we will share, it
it's
will be the
visible
same.
in my pen drive. It's visible in
Basically,
my.
basically
So
in a
ma'am, my
folder
request is
you write
immediately
down all
after
images
this
in a folder.
presentation, you kindly share this presentation with us. We will share with the participants.
Okay.
Basically, all images should be in a folder, same folder.
Sir, just give me a minute. I will try to do something else.
Please. Okay, you are sharing again. Ma'am, in the meantime, please share it us. Oh, now it is started.
Can you see now? Sir, can you see the image now? Sir, can you see now?
Yes, ma'am. Visible, ma'am.
Now it's visible.
Yes, ma'am. Yes, ma'am.
So, as I shown earlier, I presented once again. These are the 7 base units, and these are the constants which define these SI units. And what is a standard? That is a physical standard, can be an artifact which I already explained. This is the main image I want to show you. Then these are the 7 base units, and how these units, other units, are defined by these base units. So you can see here, here is our potential, that is voltage. Here is our voltage. Here our electrical charge. Here our capacitance, resistance, conductance, then current, primary. This is electric current. Now, electric current is defined in terms of charge, which we try to realize at NPL, which I have shown in the video. We have quantum phase slip. We are working on quantum phase slip phenomena and quantum current standards also. So this is our activities, how we are defining each unit in terms of SI units. So whatever parameter comes to us for measurement, we are taking this parameter to the SI unit. So our results are most accurate and most reliable within the country and internationally also. Now I will explain global metrology infrastructure. Why it is important, as I have explained already. So if you have to harmonize all the standards throughout the world to remove the trade barriers, your standard should be uniform. So for maintaining these uniformity, we have some system of measurements and some organizations are included here. The first one is the meter convention. Before invention of meter convention, everyone has another unit for their length measurement. मान लीजिए हमारे इंडिया में भी there is फलांग, there is बीघा, there is mile, there is meter. Meter is came later. Everyone has all अलग अलग units होता था. They can measure with फीता also. They can measure with some hand fingers also. They can measure with anguls also. You have listened in the Vedic era कि उंगलियों से भी measurement हो जाता था. So how we will harmonize these system? If we are different in our country also, uh, we cannot move from one place to another with these kind of scattered units. So we should have one harmonized system of units to uh, co- correlate these terms here. So meter convention was invented in 1875. The NPL was also a member of this meter convention, and we are a member of BIPM member state. So I will explain what is that meter convention. 1875, there was a diplomatic treaty which decided to harmonize all the standards throughout the world. So General Conference of Weights and Measure organized, it is called CGPM, which meets every 4 years and consists of delegates from member states. Member states are the participants of meter conventions. Then member states, governments of member states also contributing here, and associate states and economies of CGPM. Whatever countries are included here, they are also contributing in the CGPM. CGPM, every 4 years they are meeting, but CGPM has defined some CIPM. CIPM, International Committee of Weights and Measure, which divide the globe into 6 parts. So I will show what these 6 parts around the world, around the globe. So it consists of 18 individuals elected by CGPM. It is charged with supervision of VIPM. It is under the control of VIPM and affairs of the meter convention. They will decide all technical issues, and they meets every year. CIPM meets annually and discuss their requirements of each economy, what parameters they need, where they needs improvement, where they needs upgradation. They meets every year and define what we have to do next. What is the requirement of the society? What is the requirement of the industry for a particular nation? So all nation representatives, that is for here, our NPL director is nominated here. He meets every year with CIPM committee and define the requirements of industry and R&D organization within the India. We are also supporting the SAARC nation because we are actively involved in these meteorological activities within the Asia Pacific region. I will explain what these contains are. I will show in the next slides. Then we have consultative committee. Consultative committee normally chaired by a member of CIPM. Member of CIPM may be any states which is a member here, to advise the CIPM, act on technical matters, and take important role of CIPM MRA. CIPM MRA is mutual recognition agreement. It means if you're measuring in India and if you are measuring in Bangladesh, these two measurements should be same. This is the CIPM MRA, or it is live within the uncertainty band. If it is not there, then you are out of these measurement capability. So if you are saying you can measure 1 volt with an accuracy of 1 nanovolt, and some other country is saying I can measure 1 volt with an accuracy of 10 nanovolt, but the international standard is 1 volt plus 2 nanovolt, then we are in and the other country is out. So this is the how CIPM MRA relates all global standards, harmonize all global standards. So which standards come in these bars? These are in within this CIPM MRA agreement, and which are not lying within these limits, it is out from the CIPM MRA. CIPM MRA also give you the give you one confidence that your measurement are accurate, and whatever you measure here, it will be accepted everywhere, which are the members of within the CIPM MRA. So who can be the member of CIPM MRA? Only National Metrological Institutes. National Metrological Institutes is defined by the government of India, as we are defined by the Gazette of India, and we are there in the legal metrology documents also. So in India, there are two organizations which uh, directly participate in CIPM MRA. That is NPL India for 7 base unit, and BARC, Bhabha Atomic Research Institute, for radiation related metrological parameters. So these two from the India are represented here every year to define the national standards in these fields, in respective fields. So how these all things, all these coordination is organized by the International Bureau of Weights and Measure, that is BIPM. This is the International Center of Metrology and laboratory and offices at huh, service ends. So these are the CIPM countries. You can see here, this green is SIM, Inter-American Meteorological System. America का meteorological system जो भी होगा, it should be harmonized with here. It should be harmonized with here. So what is the role of CIPM and CGPM? CIPM doing inter-laboratory comparison. Asia में जितना भी countries हैं यहाँ पे, they are doing their standards measurement within these limits, and some African countries and all other countries are making within their regions, and all these results are compiled by BIPM, how equivalent or how close they are. So these are the whole globe is divided in these six regions. That is India Intra-Africa Meteorological System, which is AFRIMET. AFRIMET is here. Asia Pacific Meteorology Program, APMP. APMP, we are here in the blue one. In the Euro-Asian Cooperation of Meteorological National Meteorological Institutes, CUMET. CUMET is this red one, and European Association of Meteorology Institute, EURAMET here, and Gulf Association of Meteorology, GulfMet is here, and Inter-American Meteorology System SIM is here. So all standards and all countries within this region who are there in the CIPM MRA, they are measuring their standards and comparing their standards on the regular basis. Like we are comparing our standards with Meteorological Institute like NIM China, NMI Thailand, and all other whatever we who want to compare their standards with our standard can coordinate for this. So APMP is our coordination body. We compare our standard within Asia Pacific region. If we want to coordinate or compare our standards with other international body, we have to write to the CGPM to organize an international intercomparison. So this is the how harmonization standards carry out throughout the world. What is CIPM MRA? You can see to establish the degree of equivalence of measurement standard maintained by NMI, which I have already explained, to provide the mutual recognition of calibration and measurement certificate issued by NMI, thereby to provide government and their parties with a secure technical foundation for wider agreements related to international trade. So our final objective to remove the barriers for international trade, to harmonize the standard which directly affect the GDP of the country. So we are providing calibration certificates with CIPM MRA logo, which allow you to sell your products throughout the globe without any objection. So now this is the all about the international scenario of global meteorology. Now what is our national quality infrastructure in India? So national quality infrastructure, if we improve our standard, we can improve our quality of life. How? I will explain here by a simple block diagram. Here, three main pillars in India: ISO, ISC, Bureau of Indian Standard, who define the standards for as per our requirements. ILAC, it is Quality Council of India, three pillars: NABH, NABET, NABL. NABL for calibration laboratory, NABH for hospitals, NABET for, I think it's for, sir can tell me. Consumer Affairs, Department of Consumer Affairs, Legal Metrology, CPCB and MNRE comes here into picture. And these parameter testing and calibration labs are controlled by the Quality Council of India, NABH, NABET, and NABL. Hospitals and all these certification and inspection bodies are controlled by and monitored by Quality Council of India. So if we improve our calibration and testing and our results and our uncertainty, we can definitely improve our quality of products, enhance safety and health, and decrease environmental impact, increase international trade. So this is the final objective. Why these standards, standardization system, and quality infrastructure is required to the growth of the country. Now come to the next slide. How NPL is supporting NPL is supporting India to growth our industries, for the growth of our industries and calibration laboratories and measurement capabilities. So we have electrical and electronics metrology division. We are working in DC and impedance metrology section. We have three subdivision which has DC metrology, impedance metrology, and DC high voltage metrology. So DC metrology part will be explained by Ms. Himavati. Impedance and high voltage DC voltage I will explain after her. So I will carry over to Hema to explain DC metrology part.
Thank you. And we will start with our CMCs under this particular section, LF, HF impedance. Last one. So in case any queries in the previous presentation, you can ask that in the end of the presentation. So I will start with the CMCs of NPL in this particular division. One is the DC metrology. First, I will deal with the DC metrology. DC metrology, we have 22 CMCs. CMC is nothing but calibration and measurement capability of a NMI. So it will be displayed in our KCDB website of BIPM. That means that in case if we have a CMC in KCDB website, it is agreed internationally and the certificate provided on the name will be accepted internationally. So here we have means all the 22 CMCs has been explained here. First one is DC voltage reference standard. So usually Zeros are a basic fundamental reference standard which is used to set the reference voltage. So we have Zeros which are capable of delivering 1 volt and 10 volt with an uncertainty from 80 to 350 nanovolt. 1 volt we have 80 nanovolt uncertainty and 350 nanovolt is for 10 volt. Next is a secondary reference standards using multifunction calibrator, 8 of digital multimeter and transconductance amplifier. We have 13 CMCs. Out of the 13 CMCs, we managed to deliver for voltage, current and resistance. So voltage is from 10 microvolt to 1000 volt. Current is from 1 microamps to 100 amps. And for resistance, it's 10 micro ohms to 100 megaohm for MFC and 10 micro ohm to 1 tera for standard resistance. And for establishing these CMCs, we use multiple artifacts. One is resistive voltage divider. It is capable of delivering in ratios, that is 1:100 ratio and 1:1000 ratio. The uncertainty is around 2 ppm. Next is high current DC shunts. So we have a shunts of 100 micro ohm to 0.1 ohm, which is capable of taking current from 100 amps to 600 amps. The uncertainty for that is 30 ppm to 500 ppm. Then last one is the high resistance. Using tera ohm bridges and electrometers, we are establishing these uncertainties. from 10 megaohm to 100 teraohm. The uncertainty is in the range of 0.2 milliohm per ohm to 80 milliohm per ohm. So this is some of the basic CMC thing. And next is other parameters, that is capacity and dissipation factor. These comes under impedance metrology. The capacitance value is 10 picofarad at 1592 hertz frequency and the uncertainty is 0.6 ppm. Capacitance dissipation factor, we have 0.5 times 0.5 to 0.001 at 1 kilohertz. The uncertainty is 30 ppm. Next is AC resistance. The AC resistance uncertainty is defined from the DC resistance. So the value is from 1 ohm to 1 meg at 1 kilohertz. The uncertainty is 5 to 300 ppm. Next is capacitance, 10 picofarad, 100 picofarad, 1000 picofarad at 1 kilohertz. The uncertainty is plus or minus 10 ppm. Another capacitance range is there, that is from 1 nanofarad to 1 microfarad at 1 kilohertz. The uncertainty is plus or minus 100 ppm. Next is capacitance meters. So this is based on 0.001 to 6 times 0 picofarad. Based on ratio method, we measure these capacitance. The uncertainty is 10 to 100 ppm. Next is inductance, self-conductance, and equivalent series resistance measurements. These are intermediate value measurement. The value is from 1 to 100 millihenry at 1 kilohertz. The uncertainty is 30 to 100 ppm. Last one is AC voltage ratio, attenuation, and gain real component. So 0 to 1, this is dimensionless. Since it is ratio, at a frequency of 55 to 10 kilohertz, we can calculate this ratio at the voltage of 10 volt to 100 volt. The uncertainty is 0.05 ppm to 1 ppm. So this is high voltage CMC, that means high voltage DC parameter CMC. It has three CMCs: high voltage DC source, high voltage DC meter, and high voltage divider ratio. So 1 kilovolt to 100 kilovolt, we have a source. The uncertainty is 50 ppm. High voltage DC meter, that is also we can able to measure 1 kilovolt to 100 kilovolt. The uncertainty is 20 ppm to 100 ppm. Next is 100 high voltage DC divider ratio, that is also 1 kilovolt to 100 kilovolt. The uncertainty is 20 to 100 ppm. So totally we have 33 CMCs under this section. These CMCs are at international par, that means internationally agreed, and it is at par with international level. Other NMI, in case if you compare these CMCs with other NMI, we are at par with those NMIs. So next we can talk about DC metrology. In DC metrology, what we do generally is realization of electrical units such as DC voltage, DC current, and DC resistance. DC voltage and DC resistance are derived units, and DC current is the primary SI unit, but still it is under development. So we are using derived, based on derived units, we are realizing that electrical unit. So we do traceability dissemination to the nation. Next is maintenance of national standards of DC voltage, DC current, and DC resistance. We do give calibration services to government sector, strategic sector, and private calibration laboratories. And the documentation we maintain is abided by ISO IEC 17025 2017. So this is the traceability dissemination of DC parameters. First, we have at the primary standard to the working standard. I will explain. The primary standard for voltage is Josephson series array voltage standard. And the primary standard for resistance is quantum Hall resistance standard. Based on Planck constant and electrical equivalent charge, we define Josephson voltage as well as resistance at a plateau of I equal to 2. That I will explain it later. So current is derived from the voltage and resistance using Ohm's law. And from Josephson voltage array standard, we take the traceability of reference voltage standard, that is Zener. And using Zeners and 1 kilo ohm reference standard, which is calibrated against QHR, we calculate all, that means we calibrate all the resistance standard using ratio method. That is 100 micro to 1 tero, we establish traceability using DCC bridge. By using precision voltage divider ratio 1:100 and 1:1000, we derive the traceability for 10 microvolt to 1000 volt. Based on this, we calibrate multifunction calibrator, DMMs, ammeter, voltmeter of various ranges, and we provide traceability to industrial meters, working standards, and standard reference materials. Next is the primary standard, Josephson series array voltage standard. Josephson voltage standard is based on quantum phenomena. This is the primary standard for voltage. Almost all the NMIs in the world have this primary voltage standard. So the Josephson effect is the primary voltage. It is based on the Josephson effect. Here you can see a picture. Two superconductors are there. So this is the gray area is a Josephson junction, which is formed when two superconductors are separated by a weak link. So which allows a tunneling of electron pairs. When a bias current is applied, the junction is irradiated with a microwave radiation. Then this electron pair is generated, which is results in the voltage generation. So here, this voltage is equal to number of electron pair into Planck constant divided by 2 times of electron charge multiplied by the radiated frequency. So 2 into E by H is the Josephson constant. Based on this, if we calculate the Josephson constant value, it is 483,597.9 GHz per volt. Meaning, to generate 1 volt, you need to irradiate this Josephson junction with this frequency. So this Josephson junction is ideally considered as independent of constriction, size, and temperature. This is no noise. There is no thermal EMF in the Josephson junction. Though there is no IR drop, that means voltage drop, it is not there at all, because the steps are vertical, the alignment of these junctions are vertical, so there is no link or no chance to voltage drop or thermal EMF. So we can have a stack of voltage junction which may create so many voltages, many steps we can generate voltage. First is that in case if we are giving 73 GHz of frequency to the Josephson junction, we can generate 150 microvolt at the Josephson junction. This is based on the frequency, we can adjust the voltage from a lower level to higher level. So next is how JVS is. Here you can see, I think you can see the cesium clock. This is calibrated against our primary standard of time. That is, and this is a frequency generator. So this frequency generator is calibrated against our frequency clock. So in case if I am generating 73 gigahertz of frequency from a generator and applying it to the Josephson array, this Josephson array is situated in a helium container, means liquid helium container. This is to avoid the temperature noise, that means to avoid any noise. So we keep our Josephson junction array inside this container. So if we apply a bias current to the array and irradiating with the microwave frequency at this particular temperature, we are generating a voltage which can be measured by an voltmeter and compared with the Zener voltage. This is how Zener is calibrated against JVS. Zener is capable of delivering 1 volt and 10 volt. So in case if I am generating, that means connecting 1 volt of Zener to the voltmeter and I'm generating 1 volt from the Josephson array, we compare both of these voltage and we identify how much is the deviation from the ideal value and what might be the uncertainty of that particular value. Similarly, for 10 volt, we give 10 volt of Zener to the nanovoltmeter and 10 volt is generated from the Josephson array and we compare. Based on this method, Zeners are calibrated at NPR. Next is this is an example of NIST USA and NRC Canada. IV curve means in case if I am applying a particular current, the current is same, but these red lines shows different junctions. In case if I am applying, that is stacked junctions, series, it is in series arrangement and vertically arranged. In case if I am applying some current here, the same current everywhere. So based on the number of stackings of series arrays, we have increased voltage. So you can see minus 400 to 800 volts. The voltage is generated based on the number of junctions here. Since these junctions are very much vertical and there is no thermal EMF, there is no loss at all. So this is ideally considered a lossless phenomena and it defines our primary voltage reference standard. So this is the NPL standard of DC voltage. On the left side, you see this steel one is the helium container, and our Josephson array is placed inside this. Based on this, here you can see a small wire. We are giving the frequency using frequency generator, and other outputs are connected here. That means we are connecting our Zener. These are all the Zeners. These Zeners are calibrated against our Josephson array, and we compare Zener voltage with the Josephson array voltage using a nanovolt meter here. So this is the Zener's 732B at NPL. So we are maintaining the standard voltage 1.018 volt. The uncertainty of the Zener is 80 nanovolt, and at 10 volt the uncertainty is 350 nanovolt. Next is the next primary standard is quantum Hall resistance standard. This is also a natural phenomena. The primary resistance standard is based on the quantum Hall effect. Let me explain what is that quantum Hall effect. In normal Hall effect, actually it is defined after discovered Edwin Hall. A thin metal film is located in a magnetic field. This is a thin metal film. Usually it will be gallium arsenide substrate. So to get very much accurate results, a magnetic field from 8 to 12 Tesla, the heavy magnet, means the earth magnet, is placed here. So this thin film is placed in a magnetic field perpendicular to the thin metal film. So this is this magnetic field. So when an electric current I am applying it externally to the metal film, the electrons are deflected due to the Lorentzian force and creates an electric voltage perpendicular to the current. So if I am applying the current here, the voltage is generated here. Okay, in both ways. So this is the so-called Hall voltage. The Hall voltage UH and the longitudinal voltage UXs and the Hall resistance RH and longitudinal resistance RXs are calculated according to this equation based on the current which we are giving as input, that is known as Hall current. So here at QHR, when the voltages increases, if I am increasing the magnetic field, based on the magnetic field, the voltage keep on increases. This is the normal Hall effect. It can happen under special condition, that is in the steps of Hall voltage, so-called Hall plateaus. These are all called Hall plateaus. These spikes, these are all called Hall plateaus for practical reasons. That means for a stable voltage output or resistance measurement, we use the plateau I equal to 2. So in this plateau, our resistance, a standard resistance is defined based on the von Kisling constant. This has delivered him the Nobel Prize, von Kisling. Rk is equal to h by e square. Here also, based on Planck constant and electron charge, the resistance is defined. This numerical value is defined for, it's a constant one and it is defined everywhere. This means all the NMIs are following this value. So the von Kisling constant depends only on the Planck's constant value and the charge of the electron. These are all unchangeable. These are all fixed, and it is reproducible with an extraordinary precision of at least 10 power minus 10. So we are calibrating our 1 kilo ohm standard against this QHR. So based on this plateau, this value is generated, and we are comparing our 1 kilo ohm resistance standard against this QHR. So here, this is NPL's QHR standard. Similarly, this is helium container at 4.2 Kelvin, and we have kept our Hall resistance standard inside it to avoid that noise due to temperature. And we are comparing, this is our Q10 DCC bridge, that is direct current bridge. We keep our 1 kilo ohm standard here. We compare this plateau value with respect to this bridge when we arrive the value of 1 kilo ohm. This 1 kilo ohm standard is the primary standard with an uncertainty of 0.08 ppm. Using this, we deliver, means we calibrate all other resistance standards using our another DCC bridge using ratio method. So 1:10, 1:100, and 10:1 ratio we have. Based on this, we calibrate our resistance from 10 micro ohms to 1 tera ohm. So direct current comparator, what is direct current comparator? DCC bridge we are talking about. So initially we were using Wheatstone bridge, that is based on this ratio is equal to resistance. Unknown versus unknown we compare, and we balance the bridge by the voltage ratio, and that is of binary bridges. Now we use direct comparator current comparator bridge for more accuracy and very less uncertainty. This bridge based on the operation of equal voltage and ratioed current. Here we have a primary standard, that is we have a 1 kilo ohm standard calibrated against QHR. This we connect here, and this turns, this is internally the number of resistance. Based on this resistance, these turns will digitally set here. So based on this current and turns, the current will start flowing here. And similarly, we have another unknown resistance. So RP, here the turns, this is variable turns, NP, this is unknown. But here the core, based on this current, it will start flowing another current here. So based on this number of turns will energize. So some current will flow here. So there is a difference in current which is get known by the detector. The difference in current will be adjusted here by the variable core again, and based on this adjustable variable core, the current here left, that means standard as well as the DUC will be the same, and detector will deflect 0. That is I1 minus I2 equal to 0. Once the detector shows 0, then the bridge is balanced. So IPRP is equal to ISRS. That is how the bridge is balanced here based on this variable core DC direct current comparator bridge. Usually we use 4-terminal resistance ratio bridge for the good linearity. 4-terminal resistance up to 100 kilo ohm, we have 4-terminal resistance. Beyond 100 kilo ohm, 1 megs to 1 giga, we have 2-terminal, and beyond that, we have n-type connectors. So this particular DCC bridge is capable of measuring 1 ohm to 1 giga in the higher side, and in the lower side, it is 10 micro to zero point 0.1 ohm. So in the lower side of this is working on high current, based on high current flow, that is from 1 amps to 600 amps. In the higher range, or that means for mega ohm calibration, it is working on voltage balancing. In the normal ohm range, that is 1 ohm to 100 kilo ohm, DCC bridge will operate at we have pi CMCs using DCC bridge. The particular one is 0.1 ohm to 1 mega ohm. This is normally used for all the industries. So the uncertainty is 1.5 ppm to 5 ppm. Next is direct current standard. As all, I mean, earlier sir, Ashutosh sir has mentioned that they are trying to establish our primary current standards in various regional laboratories. But this current can be realized by various methods. First, is the primary method. It is a quantum phenomena that is given by B. Here I am highlighting here. So it is a single electron transport or a single electron pumping method. Similar quantum chip will be developed, and the current will be based on the charge and frequency. So this is a unit charge per second. We will get a current value, that is 1 ampere. So the value of the given in the definition of the ampere and the practical realization of SI unit is this. But it is still under development. So we use other two methods. One is Ohm's law method, that is based on voltage and resistance, which is already derived from QHR and JVS. We can derive the current. So using practical realization of SI units is done by voltage and ohm. These are traceable to JVS and quantum Hall effect. Next method to realize current is capacitance charging and discharging method. Based on farad as well as voltage with respect to time, we can define current. So this is also a practical realization of current. But for higher values, we are not using this method. So this method will be used for higher values, that is higher values in the meaning 10 microamps to 100 amps. In case if you are going lesser value, going for lesser values, that is less than 10 microohms, so we can use this capacitance charging method. In NPL, we have established a technique to generate and measure low current from 1 picoamps to 10 microamps using this capacitance charging method and Ohm's law method. Next is NPL standards of DC current. If you have seen NPL standards of QHR and JVS for voltage and resistance, here this is of DC current. We use multifunction calibrator as source, and this is a direct source for 10 microamps to 100 amps. Using a transconductor amplifier, we are supporting up to 100 amps. So this is a normal methodology, that is Ohm's law. If you are applying to a resistor, another methodology is this. So I am having a resistance, multiple resistance from 1 ohms to 100 tera. Using that resistance, I can able to generate variable current. For example, if I'm having a 1 tera ohm resistance standard, I am capable of generating 1 picoamps to 100 picoamps using that range. So we have several ranges of resistance. So we can measure several ranges of current for lower level and higher level. So the CMC presently available with us is 100 microamps to 100 amps using this multifunction calibrator. So we have used so many methods. That means we have artifact method. Artifact method means we have Zeners, we have DC voltage dividers. Based on that, we generate current or voltage and we measure the values. Next one is comparison method. That is, in case if we are getting a Zener for calibration, we have our reference Zener and we will compare our Zener value with the customer Zener. Based on that, Zeners are calibrated. That is comparison method. Last one is direct method. Most of the DMMs which comes here for calibration will be calibrated using direct method. So we have a source calibrated, that is our MFC is calibrated. Using this, we can calibrate the DMM. Next is some of the points which we need to remember while doing the calibration. So preliminary operation of calibration of multifunction calibrator and DMM. Most of the private laboratories and regional laboratories use MFC and DMM to calibrate their customers' DUCs, whatever it is. So we are maintaining a temperature 25 plus or minus 1 degree Celsius. Here the temperature plays a major role. In case if the temperature was not fitting in this particular point, then the meaning of calibration is not at all there if you are not maintaining the temperature, because all the values are defined for a particular temperature and humidity. So these values play important role while we are calibrating. So we maintain the temperature 25 plus or minus 1 degree Celsius and the relative humidity is maintained at 50 plus or minus 10 percentage. So next is checking the functioning of DOC. Once the customer's equipment is received at your lab, you need to do the basic checking, but whether it is having any issue and turning on, or in case any faults in the instrument, you need to identify and inform it to the customer. Next is functionality check. In case there are several ranges, some of the ranges will not work properly. Before starting calibration, you need to do a functionality check, whether how much time it is taking to come to a value, whether the proper stabilization time is given to the equipment or not. These should be observed before starting the calibration. Next is our primary. While we are doing a calibration, we need a reference standard. One or two reference standards. Sometimes we need to check whether the reference standard and DUC are under preliminary zero operation. So in case if it is not under preliminary zero operation, we need to make them zero. So, and we need to cross check whether the thermal EMF short circuit has been taken care or not. When most of the times when you are doing calibration using DMM, we have to short the ends and we need to do the thermal EMF short circuiting to avoid the offset which comes into the picture. Next one is DC current. Often that input circuit will be left open, so we need to be very much careful. And some of the times we unknowingly connect in the voltage port instead of current port. We get to know later that we have mistakenly connected this. But be sure before connecting and giving an input, you should be connecting it with the correct port. Otherwise, it will damage your voltage port. Next one is last one is 2-wire, 4-wire DC resistance measurement. The input terminal will be shorted together and then it will be connected and tested. So in case of measurement, we need to compensate for the offset. If you are not getting a zero value at the initial stage, you need to measure the zero value using the instrument, and that measured value should be included in your measurement points. Otherwise, there is no meaning of calculating value, that means the values for different points. If the zero is adding additionally in your values, you should either minus or add it to your values. These are some of the points you need to keep remembering during your calibration. So these are the services provided by DC Metrology. One is DC voltage reference standard, multifunction calibrator, from 10 microvolt to 1000 volt, and DC current 10 microamps to 100 amps, DC resistance from 1 ohm to 100 ohm. So including this and the same range here, and 1 ohm to 100 giga ohm for DMM. So including these two, that means MFC and DMM, we have 13 CMCs. DC voltage reference standard, we have 1 CMC, so 14 CMCs, and the remaining 8 CMCs here, that is DC resistance standard 100 micro ohm to 1 tera ohm. We have a few standards, means few CMCs, and for 1 tera ohm to 100 tera ohm, we have high resistance bridge CMC. So recently we have started these three calibration. One is low current calibration, that is 1 picoamps to 1 microohms. 1 picoamps means it is 10 power minus 15. Minus 12. So we are working on 10 power minus 15. The R&D is still going on, but 1 picoamps we are able to deliver. From this range, we are getting so many picometers, ammeters, electrometers, and dosimeters for calibration. This range is required particularly for health sectors. That is, radiation dosimetry defines the value of radiation dosage to the patients. So for that, we are doing this calibration. Next is RTD and thermocouple calibration using voltage simulation method. This is also we have started very recently, maybe 1 year or back, and we use ITS 90 table, and RTD, we use ITS 90 chart for resistance. Using that resistance value and voltage value, we simulate temperature using our MFCs, and we measure using the DSUs. Last one is low charge calibration, that is 1 nanocoulomb to 2 microcoulomb we do, and we have another capability that is 1 picocoulomb to 1 microcoulomb also. But this low charge calibration is useful for electric field strength calculation. Few customers are willing to take this service from us, and so thank you so much. And from this, I conclude my presentation, and ma'am will take over.
I would like to ask whether you want to ask some questions regarding this section, what we have covered till now. Anybody has any questions, so we can answer. Can you hear us?
Yes, very well.
So no question. Should I proceed further?
Ma'am, please proceed further.
Okay.
Because if there will be some questions in the chat box, we will take it in the last.
Okay.
Thank you.
So impedance metrology. How impedance is defined? I will start from the very basics. Impedance is a circuit component. It is the opposition in the flow of current, in the path of current. So it is defined as the real and reactive component R and X. It is R plus JXL. It is the definition of impedance. Here you can see in the imaginary plane, a real and imaginary part. The real part is in the direction of voltage, and imaginary part in the direction of in the 90-degree out of phase. So if you talk about the impedance metrology, lot of things comes into the picture. Impedance is not only a resistance. If you have some frequency, there should be one reactance will be there. It will be either inductive or either capacitive. So if it will be inductive, it is leading by the voltage form, and if it is capacitive, this current is lagging. So these are the impedance standards. Here you can see the resistance standard. This is capacitance and inductance standard. This is capacitance standard, and this is inductance standard. So impedance को define करने के लिए we have lot of coaxial bridges at par with other leading NMIs throughout the world. So I will give you a look about these impedance measurements at NPL India. So simple, how if we move from DC to AC, DC versus AC measurement, what changes appeared? Here, the R is represented by Z because X is come into the picture, reactance is comes into the picture. Here, if you have some resistance, there should be some capacitance also formed there because you have some material there. Material का कुछ डायरेक्टली कांस्टेंट होगा, उसका कुछ वैल्यूज आएंगे. So interconnects होंगे. So there should be some parasitic elements comes into the picture. This is C, and here if you connect the leads of a impedance or any resistance, if you are connecting leads, making some port for connection, the lead also contribute in the impedance value. And if it is DC, then omega is equal to 0 for DC, so it will not contribute for DC measurement. You will apply DC voltage, DC current and measure the DC voltage. But if you are applying AC voltage, the reactance and impedance, capacitance, inductance all comes in the picture, and defining the value of that R will be modified. So measurement affected by lead resistance, lead inductance, stray capacitance, contact resistance, interconnects, and electromagnetic interferences. So these are the combinations how these impedance standard defined in two-terminal combination, three-terminal, and four-terminal connector combinations are defined there. Here, for better precision, we are making four-terminal connections to measure a device. So these are the type of connection which we are normally using in calibrations. Changes from DC bridge to AC bridge. If you talk about DC bridge, you have voltage divider V1, V2, and you have resistance ZX and ZS are your standard resistance. You are making this measurement here. And if you are moving to the AC bridge, then your voltage source is applied derived from the precision inductive voltage divider. The dividers, resistive divider is replaced by inductive voltage divider, and simple resistance is replaced by the impedance of that resistance. So impedance changes with frequency because for inductive component it directly proportional to frequency, for capacitive component it is inversely proportional to the frequency. So impedance changes if you apply AC signals. So these are the some how we are moving from DC to AC bridge. Coaxial measurement, if we are talking about the impedance measurement, it's not so simple as a Ohm's law because many factors comes into the picture. Here you can see this is IVD, inductive voltage divider, our AC voltage reference standard. So if you have to divide some AC voltage, we are putting IVDs in the circuit. It will precisely divide that voltage up to the level of 1:1:10⁸. So we have these IVTs maintained here for precision impedance measurement, and we are making this bridge as a if we are making some interconnects, there should be some combining network which balances all the parasitic capacitance or inductance connecting in the circuit. So it eliminates the impact of these interconnects, and the standard impedance is defined in four terminal combination to get the precise measurements. So I will show here the circuit components which we are using here, and all these components are made at India, NPL India, and NPL India is within the few countries around the world. Already 7 or 8 NMIs in the world are maintaining these kind of system, which I am going to show you all here for impedance measurement. So these are combining networks maintained and fabricated here at NPL. These are in IVDs, inductive voltage divider. These are the interconnects. You can see here the coaxial cables and BNC connectors. All coaxial cables are here. We are giving measurements through coaxial cable to minimize the effect of induced EMF. If you are flowing the current through this conductor, inner conductor will flow the direction of current in the circuit, and outer conductor will provide the current back to the supply through this outer connection. So net EMF induced by the forward current in the circuit is compensated by the reverse current to the supply, so that the interference free measurement you can get with these coaxial connections. So coaxial connections comes into the picture. all 4 terminals comes into the picture, and inductive voltage dividers comes into the picture. Along with these, you have to balance the bridge for these parasitic compensation. So you have RC network for phase shifting, because if you want to balance the in phase component, in phase means in the direction of your applied voltage. If you want to balance the in phase voltage, you have to apply some phase to the circuit. So this phase can be applied to the divider side or the voltage supply side, or in the DUC side. You have to see whether phase change occurred in which direction. So this comes with an experience. It is very complicated setups. I will show in the next slides. So we have impedance parameters maintained at CSR NPL. For low frequency, we have capacitance, inductance, resistance, and AC ratio. High frequency, we have capacitance, resistance, inductance up to the 250 megahertz frequency range. This is the definition of traceability, how we are defining the traceability of impedance standards. We have fused silica reference capacitor, which is 10 perf and 100 perf values. They are traceable to BIPM. BIPM is defining our capacitance standard from the quantum Hall resistance standard through the chain of coaxial impedance bridges. Then we have transformer ratio bridge, where we can derive 1000 perf air capacitor. From this bridge, we are defining the capacitance range from 1 perf to 1 microfarad. And from quadrature bridge define the resistance in terms of capacitance. So we have quadrature bridge also. And then from 100 kilo ohm, we are getting from quadrature bridge. This 100 kilo ohm define 1 kilo ohm resistance, which is the reference standard for the calibration of our customer's equipment. So 1 kilohertz standard resistance, we are defining 1 ohm to 1 mega ohm resistance standard. These are our reference standard, which are used to define the customer's calibration standards here. So from these, here you get capacitance, all capacitance ranges you are getting here, all resistance ranges you are getting here. From these two, capacitance and resistance, we are forming Maxwell bridge. Maxwell bridge will define the inductors from 100 microhenry to 10 henry. And from this is the inductor range which we are maintaining at NPL. And we have in-house Maxwell Wien bridge, which we have developed here only. I will show in the next slides. And then we have high value capacitance bridge, where we can calibrate from 10 microfarad to 10 millifarad range, and uncertainties are 200 ppm to 1000 ppm. And we have low value inductance bridge also, which can define the inductors from 0.1 microhenry to 10 microhenry. Recently, we have established the facility for 1 microhenry and 0.1 microhenry. Earlier, we have only 10 microhenry facility. So this is our latest development. Now, at par with international level, how we are defining our standard, or how we are going to get the values with links with the quantum Hall resistance standard. This is the R&D part which we are working. I will show here the DCQHR. Then we have calculable AC/DC resistance standard, which is in the development stage. We are working on it. If we have this standard, then we have two resistance and two capacitance, which can be defined by quadrature bridge. Quadrature bridge, which will define the capacitance standard. Then capacitance will define other scaling of capacitance can be get from the transformer ratio bridges. And we have resistance scaling from the Kelvin double arm ratio bridge. Then resistance and capacitance will give us the Maxwell Wien bridge and Maxwell Wien bridge. And these resistance capacitance combination is also used to derive the low value inductance standard. So here, if you see about to relate the capacitance with von Blitzen constant through RK value, which already Hema has explained how we are getting these values, and this is absolute value which is not changed with highest precision. We are trying to linking our capacitance standards from this von Blitzen constants. So this is the traceability chart where we are working for. And these are the list of bridges which we are maintaining to disseminate the traceability to the industry and our customers. So we have 10-1 capacitance bridge, equal power resistance bridge, quadrature bridge, Kelvin double arm bridge, Maxwell Wien bridge, absolute calibration of AC voltage ratio, low value inductance bridge, and high value capacitance bridge. Range are already mentioned in the previous traceability chart. So this is our AC voltage reference standard. What it is? Here we have a divider. This is a divider which has special combination of arrangement, so that the coils, which this consists of the transformer coil like construction, and it is a multiple output transformers which are defined or designed such that no phase difference will appear at the output. So whatever voltage you are applying, you are getting exactly same exactly voltage. You will apply exactly precise voltage with a very precise voltage division. So we have range from 1 to 10 power 8. We can divide applied voltage by 1 ratio to 1 ratio 10 power 8. And with this IVD construction, I will not go into the details because it will take some time. So I will exclude this part. This is our IVDs which we are using to define our standards. You can see the experimental setup for measurement of these IVDs. IVDs are precise AC voltage ratio. Its uncertainty is the range of 0.03 ppm to 0.3 ppm, and it has 37 calibration point if you are comparing for first, second, third decades and last combination decades. If ERTL persons are there, they can know, they must have listened about this because they are coming us for the calibration of inductive voltage dividers. So this is, here you can see, this is the inductive voltage divider. This is our reference AC voltage ratio standard, and this is our experimental setup to define the accuracy and precision of the inductive voltage divider. So these are the application. It is used for the accuracy of few parts in 10 power 8. The winding in the magnetizing winding and ratio winding, when there is a very less ratio current, so we are getting ratio, very precise ratio for voltage for impedance measurement. And construction reduce the current in the ratio winding considerably, and error arising from the inequalities of leakage impedance or the section of the mill reduced by the factor of 100 in the, if we have two stage core constructions. So these are some IVDs features which we are using in impedance measurement. And application is measurement of electrical quantities, non-electrical parameters like sensors and transducers, determination of transformer ratio, calibration of AC voltmeters, and measurement of amplifier gains. These are the application of IVDs. Here you can see what is this coaxial impedance bridges. Here you can see these are the coils, current, these are the chokes which are included here to nullify the effects of voltage mismatch within the within voltage distribution within a wire. So these coils are used there, and these are the IVD. This is our setup for equal power resistance measurement. Equal power resistance bridge will compare the resistance standard 100 kilo ohm resistance standard with 1 kilo ohm resistance standard. And here we have capacitance bridge which will define our 10 puff and 100 puff fused silica capacitor will define our 1 nanofarad capacitor. So this is the setup, and this kind of setup is available at NPL, which we are using for the precise measurement of capacitance and resistance. This is the setup of quadrature bridge. Here you can see the basic circuit of quadrature bridge. Here RC combination, this R1C1 is compared with this R2C2, and we can define the, we have capacitance standards derived to C1 C2 derived to the this fused silica reference standards, and combination of R1 R2 is defined here in terms of C1 C2. Then this C1 C2 will define the R1 R2 through equal power bridge. I will show the next flow chart. The balance condition for this quadrature bridge is omega square C1 C2 R1 R2 equal to 1, where omega is frequency 1592, which will provide the omega equal to 10 to the power 4. So if you go through this equation, if omega is 10 to the power 4, C1 C2 will be in the order of 1 nanofarad, and R1 R2 in the order of 100 kilo ohm. So this how we have designed our quadrature bridge. This is maintained and operational at NPL India for the dissemination of traceability of resistance standards. Now we have 1 kilo ohm resistance standard. From there, then we are disseminating 1 ohm to 1 mega ohm through Kelvin double arm AC resistance bridge. Customers resistance standards are also calibrated through this bridge. So this, you can see here, these are the resistance which we are comparing. One is standard and one is DOC. Here you have to put the IVDs for the, one is the ratio arm, one is the one of the arm is formed by the resistance which are to be compared, And we have Wegener IVD to compensate the voltages mismatch within the circuit. We have RC phase shift circuits. You can see here one RC here with the Wegener, one RC here with the IVD, ratio IVD, and one RC here for the all phase difference within the circuit. And we are measuring, we are providing some fraction of voltage through these IVDs. If you are going to the digits of these IVDs, if it is here in the 6th place, then it is 10 ppm place. If it is in the 7th place, it is 1 ppm place, and it is 0.1 ppm place. So we can balance these bridges up to the 0.1 ppm precision. So the standard which are measured through this Kelvin double arm bridge are very precise, and the uncertainties of the 1 ohm to 1 mega ohm standards resistors are in the order of 2 ppm to 100 ppm. So this is our Kelvin double arm DC resistance bridge. Now here is a summary how we are defining the resistance standard at NPL. The quadrature bridge, it interrelate the capacitance with R1, R2. R1, R2 are the 100 kilo ohm resistance standard. Here you can see this is our balance condition. Now 100 kilo ohm resistance standard is compared with 1 kilo ohm resistance through equal power bridge. Equal power means here current is in one arm is current is I, and another arm current is maintained at I by N. So if your resistance is 100, then you have to, if your current is 1 by N, I square R will be equal here, and these I square R combination are equal if your current is 1 by 10th of the this current. So this is the special arrangement and excitation current setup which we are maintaining here at NPL to derive this setup. Then we have this resistance standards which is derived from the Kelvin bridge, and these are the resistance standards, commercial resistance standard, which are coming for us for the calibration, and uncertainty range for the customers is 5 ppm to 500 ppm. This is our high value capacitance bridge. Again, IVDs comes into the picture. We have these two devices to compare, and this is our ratio device. If we have some connection here, then we have to provide combining network to balance these phase difference or voltage difference within these interconnects. So you can see whenever you are moving to the impedance metrology, you have to take care of interconnects, you have to take care of parasitics, you have to take care of all stray capacitances, lead inductances, lead resistances, all parameters you have to take care. You have to take care of phase difference also. So these circuits are very complex, and only experienced person can take measurements on these circuits. So this special expertise is only NMIs has. So in throughout the world, only 7-8 NMIs are doing this type of measurement. So this is our high capacitance measurement range. We have recently defined these standards: 1 microfarad, 10 microfarad, 100 microfarad, 1 millifarad, and 10 millifarad. This is our uncertainty range. And you can see if we compare our results with NPL UK results, so you can see 110, 100 microfarad, 1 millifarad, 10 millifarad range. Their uncertainty at 1 kilohertz is 1 millifarad per farad 3, like this, and we are getting in this range. So we are at par with these standards. We just the objective of this data is just to show we are doing at par with international level. So this is also handmade standards which we have developed in NPL. Not me, but our seniors, which are now retired from our organization. They have designed these standards, and we are maintaining. We are continuing the legacy of their developments. So traceability of dissipation factor, we have recently established the dissipation factor in terms of capacitance and resistance standards. The series RC combination is used to define the dissipation factor standard. We have GR1620 bridge, which we are using to define dissipation factor standards, and we are capable to measure dissipation factor in the range of 0.0001 to 0.1 range. This is a unitless quantity, and uncertainty of the dissipation factor is in the order of few percentage, fraction of percentage. So this is the basic circuit science behind the dissipation factor. You can see the 10 delta dissipation factor is effective series resistance upon X. From this we are deriving these circuits. And we have inductance measurement, which I have told. We have next beam bridge where we can define the inductance. We need a combination of resistance and capacitance to define the inductance. If we have capacitance and resistance in this order, here R1, R2, these are the standard, and C is also a standard, and it is variable capacitance, one standard capacitance connected with the variable capacitor. So it's a combination of variable capacitor and standard capacitor. So when we balance the bridge, we have known value of R1, known value of R2, but C is not known because we have one known C, that is our standard, and one variable part we have applied here. So to define the inductors exactly in terms of this capacitance, we have to calibrate each time this combination with our GR1621 bridge to get the precise value of inductor. So these are the combination which we are using to define our inductor. These you can see here from the table, 100 nanofarad is keep constant fixed value, and R1, R2 are varying to define the value of inductors. 100 microhenry ke liye we have some combination of R1, R2 like this. 100 micro to 10 henry we are defining in terms of capacitance and reactance, capacitance and resistance. The uncertainty what we are getting for inductance standard is 55 ppm to 500 ppm for our standards, and customers we are providing around 100 ppm for the 1 millihenry, 10 millihenry and 100 millihenry range. And for higher values of inductor, the uncertainty is quite high, little bit higher. So this is the recent international intercomparison which we have participated. Capstans, we are starting from 1986. Now till date, we are participating in various international intercomparisons, and these are the list of this comparison. Now I will go to the high voltage metrology facility, what we have. So we have high voltage Josephson voltage standard. The uncertainty is 80 nanovolts, and from this we have DC voltage reference standard with an uncertainty of 1.6 millivolts, and DC divider ratio and uncertainty of 0.7 millivolt. And we have DC calibrator, its uncertainty is 3.5 millivolt per microvolt per volt, and high voltage resistance we have 10,000 ratio 1. The uncertainty of the high voltage resistance divider is 20 microvolt per volt. Then we have high voltage DC source, the uncertainty in the range of 50 microvolt per volt, and calibration of high voltage standards. We have high voltage probes, divider, source, and other kilovolt meters. We are providing services for these calibration. So we are going to add shortly. We are providing services to the nation, Ministry of Defense. These are our customers. Department of Space, Ministry of Consumer Affairs, Ministry of Small and Medium Industries, Quality Council of India, Ministry of Electronics and Information Technology, Public Sector Undertaking, Bhabha Atomic Research Center recently added. We have developed picoampere measurement capability for them, and other institutes and factories are also coming to us for the calibration requirement, and we are trying to support with our R&D services. So these are the reference. Now the calibration, at last I conclude with calibration and measurement capabilities are the CMCs at par with international level at NPL India. Calibration services with highest precision in the country and maintains national standard directly linked to SI units. Calibrated here is expected everywhere. So thank you for your attention. So if you have any question, you can ask. Thank you.
Thank you very much, madam, for your kind and brief presentation. Actually, we could understand a lot of things which we are not aware earlier. And I hope that if I will get the queries from the participants in WhatsApp group or later on in the mail, I will forward it to you. Santoshji, can we take the photographs?
Sir.
Oh, please. We have to make the participants panelist, right?
Yes, sir.
All the participants are requested to kindly switch on their camera. And keep the mic of, if you want to ask anything, you can ask. If you have any doubt and you want to discuss with the experts, you can ask the questions.
Not only of the fundamental concepts, we are ready to answer any questions regarding calibration procedure or calibration difficulties also.
पर वीडियो बहुत कम ऑन है, वीडियो ऑन करा
No
दीजिए.
problem. Santoshi, whatever is available, you kindly take the pictures so that we can close this session. Next week, I am planning to have the present lecture on, basically, in India, we are having a new facility of testing of gold in the jewelry, actually, not gold, jewelry testing. We are developing this system, and we have also made the hallmarking system. So the World Gold Organization, with the World Gold Organization, we are planning to have a complete presentation in the next week, how to develop this testing facility. There are basically two methods. One is destructive and the another is non-destructive method through X-rays. So how to test and what are the equipments required, we will do it in the next week, maybe on Sunday, not Saturday, maybe next Sunday, and we will share the program in the WhatsApp group very soon. I hope with this we can close this session. Thank you very much, ma'am. Thank you, Dikshit sir. Thank you all the participants and the NIC team which is helping us. Thank you very much.